Hello and welcome back to another tutorial made by UGA Big Data. Today we're going to be looking at running a CPU job on the Zcluster and a GPU job on the Zcluster, which is running on NVIDIA's K20X graphics card. So let's go ahead and get started. First step is to go ahead and open up your terminal windows and go ahead and log into the Zcluster. So I've already had my public and private key set, so all you have to do is SSH Zcluster. And now we're logged into the Zcluster. I've created a few folders here for projects I'm working on. And we're going to be taking a look at a Quicksort CPU example here. So let's go ahead and move into that folder. And we have a C source file there. So we'll go ahead and take a look at that. Basically, this program runs the Quicksort algorithm on 1 million elements. We'll go ahead now and compile this program. Now there's different ways to compile programs since they're running on the Zcluster. Now for C, they recommend the PGCC compiler. So we'll go ahead and use that one. So the way we do that, we can create a makefile here, which the makefile just compiles it. So it's PGCC, the C source file, and your output source name. So it's going to name it the Quicksort CPU. So when you run it, you can do /Quicksort CPU. So to do that, we just simply write. And once this compiles, we need to go ahead and create a shell script that allows us to run this job on the Zcluster. So to go ahead and do that, we need to see what type of systems Zcluster actually has. So the Zcluster has a few different types of systems you can run it on. The main one is the RCC-30 days. And this one has 75 CPU cores with a max runtime of 30 days. All of them actually have a max runtime of 30 days. So this one is just CPU, and the few other ones down here are the K20X graphics cards. So we're going to take a look at those later, but we're going to be using the RCC-30 days. So we'll go ahead and take a look at that one. Go ahead and change directory to the previous directory. And we've already created a shell script here. And we're going to take a look at that. The purpose of this bash script is to queue the program on the Zcluster and execute it. So what it tells the Zcluster to do is to change directory into the Quicksort CPU directory and then run the Quicksort CPU executable and redirect the standard output to an output file. And also while we're doing that, we're running the entire program through a time executable which will record the time outputs. So once we have this created, all we have to do is exit out, and we need to go ahead and send this job to the queue. So to do that, we use a program called QSub, and we use -q, and the actual system you need to be running this on. So we'll go ahead and look back at the systems, and we're going to be running this on the RCC-30 days. So we can just go ahead and copy this, and go back to our terminal window, and we're going to just paste that in there. And of course, our shell script, so that's Quicksort. And click enter. As you can see, this job has been submitted to the Zcluster. So now to go ahead and take a look at the job in progress, we use QStat, Q-S-T-A-T. As you can see, the job is not in the queue. And the reason why it's not in the queue is because the job finishes so quickly that it doesn't really exist in the queue. We'll go ahead and take a look at the output that it generates. So the Quicksort CPU.sh, .e, and the .o. One is error, one is the outputs. So we'll go ahead and take a look at those. And as you can see there, we have our time from our output. So as you can see there, here is the real time, the user time, and the system time. So on average, it takes about 1.6 seconds to run this program. So we'll go ahead and take a look inside of our output, where we redirected the standard output to the output file. So we'll go ahead and go into this Quicksort directory, and we'll go ahead and take a look at the output file. The elapsed time is slightly different than what we have computed by the time executable, and the reason why is because the program itself has to initialize data, which is create the 1 million elements, it has to run the program, and it also has to validate the results to make sure we have sorted all those 1 million elements. The reason why we use these breakpoints or checkpoints in the code is because if the system goes down before the job is completed, we want to go ahead and have those intermediary results. And for example, when we redirect the output to an output file, we can see those intermediate results. So for example, if the program goes down, something crashes, or the system goes down for maintenance at a undesirable time, you still have those intermediary results to go ahead and look at and pick up where you left off. So we'll go ahead and take a look at the actual job report. So there's another command for that. That's QACCT, and then J for job, and we have to go ahead and find the job ID here. So we'll go ahead and scroll back up here. Copy this one here. Paste it down there. And this takes a while, so to give it some time. Okay, there we go. That printout, that actually took a while for it to generate there. Basically what this does, it prints out the information about the job. Information about the queue name, which actual compute node, the actual physical node that I was running on, some of the time information, and then some of the CPU information that it's print out. So you can use that as well to look at the job's performance, as in CPU and some other factors. Now let's go ahead and take a look at a running job and see what resources we have to monitor a job that's running. So we'll go ahead and use QStat again. And as you can see there, we have a job running, and this job was submitted on 5/30/2014. Today is 6/4/2014, so it's been running for a couple days now. So we'll go ahead and take a look at that the same way we use the QACCT command. So we use qstat-j, and go ahead and copy that job ID, unless you want to type that in manually, and click enter. Now this will go ahead and print out all the information about the job. Now, this stuff here is not very useful for me. It may be useful for you, but certainly not useful for me. So I'd like to go ahead and get rid of some of this stuff here that's it's kind of annoying to see. So we'll go ahead and copy this here, and we'll go ahead and we'll be piping this through a grep function, or grep, whatever you like to call it, and we use -v. This is the easiest way I found to do it, which basically inverts the command. So it prints out everything but those two items. So we'll go ahead and use that and do slash. So this allows you to AND. This is the AND function, or the OR function, excuse me. And SGO path. Okay, this that's pretty nice. Gets rid of all the stuff there. Basically, this gives you all the information about the job that's running. Gives you information about the hard resource limit. This is important. This runs on one CUDA card. It gives you some CPU information, some memory usage, I/O, virtual memory, max memory, some other information here. Gives you who your storage device is, the PAMPs, storage, and some other information. Pretty useful. So if you use this command, you can just keep hitting this, and some of these numbers will keep rotating as long as your program is running. But that's for running jobs. So QStat basically gives you all the information there. And take a look, and if you have multiple jobs running at the same time, obviously they'll show up right there. Now let's go ahead and look at running a GPU job on the Zcluster. Now I've created a test folder called Quicksort. Now this is an example program from NVIDIA's CUDA driver. So we'll go ahead and look at the README here. This says you need CUDA's dynamic parallelism. The way we do this, we just simply type in make, and the make file already has all the targets in there for us. But before that, we'll go ahead and look at the make file. We need to go ahead and make sure we have the settings correct for the path of the CUDA library. Let's scroll up here. Scroll down to the first line here. So the CUDA path here, you need to make sure you have the CUDA path for the current toolkit. For example, right now we're running the 5.0.35 toolkit. So if that changes in the future, you'll have to go ahead and go in there and manually change that to the newer toolkit. So go ahead and exit out of there. And we'll just type in make. It's going to build our executable. Okay, as that's finished, we'll go ahead and do an else command. You see we have a Quicksort executable in there. So let's go ahead and go back out of directory. And as you see, we already have a Quicksort sh script created. So we'll go ahead and take a look at that. Now, the Quickshort script is a little bit different because you have to export the path of the CUDA toolkit. And for this program, I created a now variable, which allows me to write the output source path to a output file appended with a now argument. So we'll go ahead and exit out of that for now. And now let's go ahead and run the job. Now to run the job, it's the same as the previous CPU examples. So q sub dash q, and you have to find the system you want to run on. We're going to be running it on the Kepler system, so we'll go ahead and copy this, paste that in there, and we'll give it our quicksort .sh shell script. Click enter. Okay, as you can see, our job has been submitted, so we'll do qstat. And as you can see there, there are 2 jobs running. The other job, it's been running for a while, but you can see our second job, we've just submitted that job. And the common states that the job can be in, which is R, which indicates the job is running. QW, we weren't able to catch that this time, which means the job is pending to be run or queued waiting. And EQW, which means something went wrong with your systems. Let's go and check on that again. Okay, as you can see, the job has finished, so we'll go ahead and do an ls command here, and we'll take a look at what output is generated. So we'll do a cat. Okay, there's no errors or no output. Now we've created an output file, so we'll go in the Quicksort folder and take a look at what that generates. Well, as you can see here, we have a few messages that come up. It says it's running on the GPU, and that's a Tesla K20XM GPU. It generates those 1 million elements. It runs it on the GPU kernel, validates the results, and brings us our elapsed time of 27,973 milliseconds. Of course, you can look at the job statistics by using QACCT-J and the job ID. So we'll go ahead and find where the job ID is here. Copy that and paste it in there and wait. Okay, so there we go. We have the statistics available, and same as before, just some information about which actual physical node it runs on, some data information, and your CPU memory I/O usage. And that concludes this tutorial for using a CPU job and a GPU job on the Zcluster at the GACRC.